Today we're going to be talking about trigonometric integrals. So specifically, this is going to be the product of two trig functions integrated. We have different techniques depending upon which functions they are and also the powers of each of the functions. So let's start with sine and cosine. So sine is raised to the mth power and then cosine is raised to the nth power dx. So what you're first going to do is check to see if either power is odd. If one of them is an odd power, you're going to save one copy of that function. So for example, if I have sine squared x cosine cubed x, I see that cosine is raised to the third power, and I'm going to basically save one copy of it. And then convert the rest. We're going to convert the rest using one of the Pythagorean identities. In this case, sine squared plus cosine squared is 1. So cosine squared is 1 minus sine squared. We are then going to use u substitution. And we're going to do u equals whatever the other one was that we didn't save. So because we saved a cosine, we're going to make u equals sine x. And du equals cosine x dx. This is why we saved a copy. We have a perfect copy of du here. And so when we plug in our u's and du's, we should get a successful u sub and something that we can integrate. Distributing the u's. This just becomes power rule. And then we're going to go ahead and substitute what we defined as u. So again, if either is odd power, you save one copy, convert the rest, and then whatever you convert it into, that becomes your u. Now, so if this were sine cubed, cosine squared, it would work exactly the same way. What if both are even powers? Well, I don't know if you've covered it in AB yet, or in a previous calc class, but if we have an isolated sine squared or an isolated cosine squared, we have a way of integrating that, and that is to use a power reduction formula. So if they're both even power, what you need to do is use power reduction. So your power reduction formulas come from the formulas for cosine 2x. Just solve for the squared term. And so what we can do is use our power reduction formulas to immediately substitute for sine squared and cosine squared. Converting either sine squared to cosine squared or cosine squared to sine squared isn't really going to help. This is a difference of squares, so I can multiply that as 1 squared minus cosine 2x squared and bring out the 2's. Now if you want, you can convert this to a sine squared. It doesn't really get you a ton, but it saves a little bit of algebra. And then, because we've got a trig function squared, or a sine squared, we again apply the power reduction formula. So 2 times our original angle, so that's 4x. Pulling out the 2 again. I have something that I can integrate now. So if they're both even powers, it's a little bit more work, but it's not terrible. What about if we have secants and tangents? Well, this is going to work a little bit differently. We've got a couple of different cases. I'm going to keep track of this using a chart. Let's say this side is secant and this side is tangent. And let's say I've got secant can either be even or odd power, and tangent could be either even or odd power. Let's say secant is even power. If secant's even power, you're going to save a secant squared, and u will be tangent x. So let's say I have secant to the 4th x, tangent squared x. In this case, it doesn't really matter if tangent's odd or even power. It's going to be easiest to save a pair of secants if secant's even power. So this is going to apply to both boxes. So I save a secant squared. Just tuck it over here with my dx, and then convert this. Remember the Pythagorean identity for secants and tangents is 1 plus tan squared is equal to secant squared. And I'm going to do u equals tangent x du is secant squared x dx. That's why I saved a pair of them. This will make an exact copy of what our du should be, given that u. Multiply this out again. Integrate. And then plug in u equals tan x. Okay, so that covers these two cases. If secant's even power, regardless of whether secant or tangent is even or odd power, this is probably the way you want to go. Now what if secant is odd power? Specifically, if secant is odd power and tangent is odd power, we're going to save a secant x tan x, and u will be secant x. Unlike the previous case, it does not cover this case. We'll talk about this at the end. So if both secant and tangent are odd power, we're going to save a secant x tan x, and u equals secant x. So let's say I have secant cubed x tan cubed x dx. So it says save a secant and tangent. I'm going to use my Pythagorean identity to convert tangents to secants now. U equals secant x, du is secant x tan x. This is an exact copy of my du. I replace my u's and du's. I'm going to skip ahead a little bit. When you distribute and integrate it, you end up with secant to the 5th x over 5 minus secant to the 3rd x over 3 plus c. Okay, what about this other case? If you have an odd power of secant and an even power of tangent, it's a little trickier. I think Stewart basically says you can try a bunch of things. You can try integration by parts, you can try these other things, but it's going to be less likely for you to encounter this problem just because it is a little more problematic. What I will do is show a quick example of how this will work using as simple an example as I can. So let's use the case of secant cubed x. And I think the strategy, if you do have a product of secant, of an odd power of secant, an even power of tangent, is to convert all your tangents to secants immediately, and then try a variation of what I'm about to do. What I'm going to do is I'm going to split this up into secant x and secant squared x. And I'm going to apply integration by parts. U equals secant x dv equals secant squared x dx. Again, this looks like a derivative. This looks like something I can differentiate, but it's hard to integrate. This looks like something relatively easy to integrate. So it doesn't exactly follow Lipti, but the basic principle of dividing the integral into something relatively easy to integrate and something relatively hard to integrate still applies. Let me calculate my du and my v. So if I apply this, again, this side is going to be secant cubed x equals u times v minus the integral of v du. Now I'm going to convert tangent squared to secant squared minus 1 using my Pythagorean identity. And simplify. And then split apart this integral. Secant x times secant squared is secant cubed. Secant x times negative 1 is negative secant x, but with the negative here, we'll turn that positive. Why did I do this? This is a match for this side. So I'm going to add that over. This, although a little weird, we did learn the integral of this in Calc AB. It's going to be natural log of secant x plus tan x. So I'm going to add that over. This is, again, natural log absolute value of secant x plus tan x. Comes from a very clever multiplication of the top and the bottom by secant x plus tan x to turn the bottom into u, the top into du. I'll go ahead and add a plus c here. And then, just like the case with e to the x and a trig function, we added it over, got back the integral we had originally, added it over, and divided by the coefficient to get the answer. And c divided by 2 is just another c. So, in the rare case that you have an odd power of secant and an even power of tangent, your best bet is to try this strategy. Convert your tangents to secants, multiply it out, and split it up using saving a secant squared and attempting to do integration by parts. Perhaps exactly once. Okay, hope that helps.